This lecture, I would like to talk about the statistical decision theory. And in this lecture, we would like to develop the relationship between the samples and population. Okay. So, yeah. So we would like to develop a relationship between samples. So a sample is a set of measurements. So the sample size will be n, and we will be calculating the mean value of the sample, and we will also calculate the variance in the sample values, and we would like to relate these values to the population parameters. So population, the size of population, which is the parameter values established with a large number of observations, and it generates a population mean value mu and a population variance value sigma squared. So we will assume that the population and sample measurements, they are normally distributed. So a normal distribution is associated with population about mu value and with the spread determined by sigma squared, whereas for sample it is distributed normally about x bar and with a variance value of s squared, and the sample size is n. So we found that the we learned about the z value, that in normal distribution for one observation it is x minus mu over sigma, and in case we would like to see the average of n measurements, then the x, one single value, will be replaced by x bar, right? Which is a mean of n values, n sample values. So it is like xi over n. So in this case, the variance, in this case, the variance s, or we say s, or which is the sigma value in x bar, it is related to population by sigma over square root of n. For variance, it should be squared, and then there is going to be square, and then there is going to be the only n divisor. So we are going to use these relationships while developing the statistical decision theory. So let's see the stuff we have. So decision theory is about saying something about a process using a set or two sets of measurements. So uh, this is a representative uh, set of instrument that we use in engineering. So okay. So the decision theory has a name. Also, we refer the name statistical inference, that from sample measurements, what we can say about the population in terms of that the process is operating normally, or there is some sensor error, or there is some determinate source of error beyond the random errors. So it is to identify the scale of random errors and to address the problem in case if it gets beyond the random error scale. So we will define the hypothesis, which is a kind of a statement that there is nothing wrong with the process, so there is nothing to worry about. And of course, this can be established by, again, by defining a confidence interval. So, in short, if the values fall within the confidence interval, we are likely to interpret that things are operating normally and there is nothing to worry about. But if the values from the sample mean, if they get beyond the confidence interval, then we are likely to interpret it as there is a determinate source of error. So I will pick up the examples from these two sources, one by Professor William J.D. Corsi's book, which is the reference book for my class, and also I will pick up some of the examples from the website, from this freely available resource by Professor David Harvey. So let's start with the simplest experiment, in which we have the simplest instrument, that which is the toss, which is the coin. So tossing a coin, and let's consider the problem of tossing a fair coin 100 times. So in this case, we have the mu value equal to NP, since it's a binomial process. So 50 is the mu value, and sigma value is NPQ, which is plus minus 5. So with this problem, as the mean gets greater than 50, so we can calculate the estimates of probabilities for any number of successes, like 60 successes, 70 successes, 40 successes, by using the binomial formula, as well as we can use the we can use the normal distribution about this mean value and sigma value. It's a modality of normal distribution that when the mean value exceeds a value 20, then the binomial probabilities can be calculated by a normal distribution table, by considering uh, the mu value and sigma value of the binomial distribution. This modality has been explained in a separate video, whose link is available over here, and I will post that one in the video description. So if we proceed like that, if we toss it 100 times, then there is a kind of a weird result, that in 100 tosses, the probability of getting 100 heads, it is around 10 raised to the power minus 30. So this is a very, very small number. So we have to establish that which of the events are more likely, and we have to identify the events which are less likely. For example, what is the probability that we have beyond 80? So let's calculate that. So I will calculate it in a Microsoft Excel sheet. So for example, I have a mu value equal to 50, which is this case. Say n trials are 100, and the probability of success is 0.5. So mu value is equal to n times p, which is this one, and the sigma value, it is square root of npq. So n times p times q, which is 1 minus p, and that's it. So it is 5. So if I would like to get the probability which is beyond the value x equal to 80, so let's use this modality. Okay. Um, uh, First, by binomial distribution. Well, as a matter of software, it is not a big deal. Uh, so I will calculate, it is 1 minus. So By the way, I'm looking for a probability of x such that x is greater than or equal to 80. So it is equal to 1 minus, I can calculate the sum probability. So I use binomial distribution, and the number is up to 80, and the number of trials are n. Says d $3. Okay, it has been rightly picked up, and then $2 for probability, and I would like the cumulative probability. So it is 1.35 times 10 raised to the power minus 10. And now, if I calculate it with the normal distribution formula, so probability x greater than equal to 80. So it will be again 1 minus, now with the normal distribution formula, normal dot distribution, and I have to use the mean value, so $4, and the standard deviation $6. Okay, and then I will choose for cumulative, so true. Okay, okay, x mean value. Okay, I have to pick up an x value, so x value is 80, and that's it. So the number has the similar order, 10 raised to the power minus 10. So the modality is kind of justified. So this is now a problem that we found. The probabilities beyond 80 are very, very small. Likewise, on the left side, if we look for the probabilities, so less than 30, the similar small probabilities are possible. Therefore, we have a strange problem that in our experiment, if we get the number of heads, say 70, so if we want to consider our coin as a fair coin, the probability is very, very small. However, if we interpret it other way around, that it is a different coin, or the coin has been morphed, or it has become loaded, so that it is now producing more heads. So we have now two kind of interpretation, either to consider a 75 heads producing coin in 100 trials as the fair coin, or we interpret it that the coin has become loaded, that it is now producing more heads. So that's the condition that we define in the hypothesis, that it is either whether it is the still the fair coin, which means the conditions have not been changed, or we interpret it otherwise, that it indicates the change, or the outcome of the experiment indicate that it is no more the same process as it was before. So we have to investigate the determinate source of error. So that's the fundamental of hypothesis defining. So if I summarize, that if I would like to consider the same 100 trials, and the outcome I get is 70 heads, so is it reasonable to believe that the coin is fair with the probability point, point 0.5 for head and point 0.5 for tail? or it should be interpreted with the with the belief that the probability of head has changed to zero point 0.7, therefore it has generated more heads. So we are going to relate the probabilities with the um, probabilities of the outcome to the fundamental probabilities. So this is the picture of the hypothesis testing. So we define the confidence intervals, the interval for the acceptable value of single observation or a sample mean. So we start with the single observation, and we will recognize that a single observation um, is going to create problems for us. Therefore, we repeat the measurements. So then we define the significance level, which is the complement of confidence interval. So the interval beyond confidence interval is the significance level. So like if the 90% is the confidence interval, then the significance level would be 10%. So the values falling here must be interpreted as unlikely. Then we further define the observed level of significance as p-value, and the given level of significance or the criteria for accepting the hypothesis for a particular confidence interval is the given level of significance. Well, this will reveal in the coming examples. So, okay. So here the confidence interval from a set of measurements, we would likely to define uh, the standard deviation in that as the population standard deviation over square root of n, as I mentioned earlier in this lecture. And then a critical value of C will be defined. So like we define x bar plus minus 0.6745 times sigma. So there is a 50% probability that the true mean is included. So the value of ZC defines the width of the confidence interval. So from the sample measurements, we would like to interpret that how far is the population mean from this sample mean. Similarly, if we consider ZC equal to square root of n, so that we have x bar plus minus sigma, then there is a 68% probability. If we look for the 90% confidence interval, therefore we have to consider ZC over square root of n as 1.64. So these are the standard ways to define the the uh, errors and the confidence interval to observe the population mean around the sample mean for a sample size of n. Okay. So I hope the students are familiar with the normal distribution. Okay, this is fine. So a normal distribution is a symmetric distribution, and we define the standard normal distribution with a mean value 0 and a standard deviation of 1. So we have the density function for a normal distribution with its height values, the and in order to get the probabilities that a value lies between two values of z, we have to calculate the area under the curve, which is possible with the help of tables or software. So if we look at the normal distribution and we define the 5% confidence interval, so it means It means we are talking about two standard deviation interval. So if the values fall within this interval, like these blue dots, so they will be considered as acceptable values, indicating that the variation experienced in these values is of random nature, and there is nothing to worry about. And if the values fall within the significance region, like these red observations, so we can interpret it that there is some determinate source of error. So similarly, if alpha is defined 10%, then we have a bit less confidence interval and significance level has been increased. In some hypothesis testing, when we are interested in looking for the in the variation in the mean to lower values, so we can define the significance level in the lower tail. So if the 5% is the significance level, so we have 95% confidence interval, which is uh, above this 5% area in the lower tail. So for this observation which falls uh, within the significance level, it indicates that there is some determinate source of error which has reduced the actual mean value. And if the values belong to the confidence interval, then there is nothing to worry about. Similarly, the uh, significance level can be defined in the upper tail. So we will interpret accordingly. The values falling in the significance region will suggest that there is a visible change which needs consideration for further exploration, and otherwise we are going to consider it as a random variation. So by defining the confidence interval, we can say with our sample measurements with mean x bar, the population mean value is likely to be observed with the confidence interval probability uh, within the lower limit and the upper limits defined by x bar minus zc times sigma over square root of n to x bar plus zc times sigma over square root of n. So we say when x bar is observed over here, then within this confidence interval, these values will define the lower limit and upper limit of the population mean value. Okay. So let's see then we have the hypothesis definition. We define the null hypothesis. uh, it's a statement which says the observed value or sample mean value is not significantly different from the population mean value. So of course this is going to be true if the sample mean value predicts the population mean within the confidence interval, and the difference is expected in routine measurements. So that is the null hypothesis, which means there is nothing to worry about. The process is operating as it was designed. And the alternate hypothesis, H subscript alpha. So the observed value of sample mean is significantly different from the population mean, and therefore it's not a routine variation or we say that this variation has some determinate source of error which needs further exploration. So let's see an example. So the statement is the percentage metal in the tailing stream from a flotation mill in the metallurgical industry has been found to follow a normal distribution. So this is our assumption. Uh, when the mill is operating normally, the mean percentage metal in the stream is 0.370 and the standard deviation is 0.015. So we have adopted the population parameters. Now, a plant operator takes a single specimen as a sample and finds a percentage metal of 0.410. So 0.410. So it's a higher value than this mean. So does this indicate that something in the process has changed, or is it still reasonable to say that the mill is operating normally? So we have got just one observation. So we will see its scale of variation. So we define the hypothesis testing, that the null hypothesis is that the mean value is same as it was when the mill was operating normally. And alternative hypothesis is that the mean value has been changed. So upon this observation, we define the z value x minus mu over sigma. It is 2.67. So about this z value, we can find out the probability. So the probability is 0.9962. This is from the statistical table. And if we calculate the corresponding probability from the other side, which means the upper tail probability, so it is 0.0038. So since this was just one observation, so we can say that such observation, if they are observed on both sides of the mean value, then the total variation could lead to a p-value of 2 times of this value, which is 0.8%. So which is less than 1%. So if we consider, for example, a significance level of even 1%, then the p-value falls in the significance region. So let me draw that one for a clarification. Okay, so this says that if I develop the normal distribution, so if I draw, say, 1%, a total significance region. So let me draw that one, that the total area in the tails is 1%. So zero point 0.5 is the value for alpha is 1%. Therefore, 0.5 is the value for alpha by 2, and this is same alpha by 2. Our total p-value was turned out to be 0.8%, which means p by 2 is equal to about 0.4%, and likewise it is here. It means the observation is going to fall in the significance region. This is the observed level of significance, whereas the given level of significance is higher than that one. Therefore, with this one observation, it indicates that there is some problem. So generally, our decisions are based on more measurements. Therefore, let's see the second example. Okay. So it is very important that a certain solution in a chemical process have pH of 8.30. The method used gives measurements which are approximately normally distributed about the actual pH of the solution with known standard deviation of 0.020. We decide to use a 5% as critical level of significance. Okay, so we have got the population parameters. We got the 8.30 value and the standard deviation and the critical value of significance. So we found n equal to, okay, these are the population things. Then suppose that now our sample consists of 4 determinations giving values of uh, these values. The sample mean is 8.32 with 4 measurements. So now we will calculate z value, and we will consider the instead of sigma, we will be using the observed standard deviation in the sample mean. So which is the sigma over square root of n. So it is 2. So if we calculate now the p by 2 as a observed significance level, so it is 4.6%. So 4.6% is smaller than the given significance level. Therefore, this variation says that the uh, population mean has been changed. So we can calculate accordingly the confidence intervals. So for confidence intervals, we will use the relationship as explained earlier. It is x bar plus minus z alpha by 2 times sigma by square root of n. So there are two further definitions. So I developed a picture. So if we consider two probability distributions. So one is the red one, which represents a population that has a mean at the center of the peak, and it has a variance value. Similarly, there is a blue distribution, uh, which has a peak value around 8.0. So now if the observation is the sample mean turn out to be this red dot. So it falls here, and it is explained with a probability in the red distribution, which is population 1, and also it can be explained by a probability in population 2. So it means such an observation is possible with a mean value around 7 in this picture, in this example. And also such an observation is possible with a distribution in which the mean value is 8. So now we can put this red observation either to the red distribution or to the blue distribution. So if we define our process with reference to this red distribution, and we define the level of significance as this indicated by this cyan color, and the observation is over here. So we are more likely to interpret this observation as a member of the population 2, which is the this blue colored distribution. And it can also be accepted as as an observation of the process whose center is at 7. So if we reject this one, which is the conclusion of our alternate hypothesis, therefore such an observation is considered to be as a false negative with respect to our population 1, that we are going to consider it as a member of blue population is population 2. So rejecting a true value is a false negative thing. We call it type 1 error. The other type of error, okay, let me add another comment over here, that while selecting the significance level, we have made a slight mistake, and it was a true measurement, which was indicated of a random error, but while defining the significance level, we have put that to the determinate source of error, and we considered that the mean value of the population has actually changed to 8.0, whereas it could be interpreted other way around. So however, this compromise is going to be always there because we have to move with some value of significance level. Similarly, there are going to be type 2 errors, so which is accepting a false value. So a false positive term is used to indicate that kind of thing. So, for example, on similar lines, if we have an observation like this green dot, so it can be identified as a member of population 1 or a member of population 2. When we consider it a member of population 1, then it indicates that there is no change in the condition of the experiment or no change in the population mean, and the observation is a representative of random error, uh, as it falls in the confidence interval of population 1. However, uh, it can also be identified as a member of population 2, which says that from the reference distribution, the population mean value has been changed. So if we interpret this green dot as a member of red one, which is likely uh, uh, consequence of our level of significance definition, since it belongs to the confidence interval of the population 1, so we are likely to accept it. However, if it is indicative a of a true variation in the mean value, and it must be accepted as a member of population 2. So in this case, we say that we have accepted a false value. It was a member of population 2. So that's going to be the compromise in type 2 errors. So type 1 errors and type 2 errors, they are always going to show up whenever we put a when we define the confidence intervals and the significance levels. So they are very important while defining the properties and characteristics of sensing devices or sensors. So however, that's going to be the compromise, and that's the terminology, and that's the way we interpret the false negatives and false positives. So the type 1 errors, there is also a good analogy that sometimes when we put our right cards, ATM cards to machines, and they reject it, so that is going to be a, if that is going to be a false negative kind of thing. However, sometimes uh, sometimes, well, it is not very likely for the ATM cards, but sometimes where the persons are going to identify the at the gate. So sometimes people show them a different card, so they allow them to enter. So that is a kind of false positive that the card was not true, but it serves the entry. So that's a kind of analogy for the type 2 error. So with this, I hope my students and other listeners, if they are, they can attempt the problems of hypothesis testing, which are related to normal distributions. In the reference book by Professor De Corsi, these problems are relevant, and they while attempting these problems, I really believe that the students will learn a big deal.